Guys, what we're going to cover in this video is moderation, which is a complement to our mediation lecture. And so be sure you understand the difference between these two. And in this video, I'm going to focus on interactions. And so we're going to use the QuantPsyc package in this one. No lies this time. I say that in the mediation video. I was wrong. So QuantPsyc is our package of choice. I have another video on how to do this manually by hand, which is really helpful if you're trying to get further in moderation. Let's say you're doing three-way interactions or more, or using control variables. But QuantPsyc is a really great way to do some simple moderation to get your feet wet. So this is for my advanced statistics course. Let's get started. And so I'm going to jump right in here and talk about how to do interactions with continuous variables. I could mix and match here and have some continuous and some categorical. Additionally, if I did completely categorical, it might be easier to switch to ANOVA. But let's say, and I just wish I could remember where I got this example from, maybe the Tabachnik book, don't remember. But let's say that you have to read books for the course that you're in, and it's the number of books a person read for the course, how many times they went to class, and then we're also going to use that interaction between books and a class attendance to predict their final course grade. So we're thinking that maybe as you read more books and go to class more, you get a better grade, which implies that an increasing level of books and an increasing level of attendance result in better grades, rather than just one or the other controlling for themselves. Okay, so let's look at the interaction between books and attendance and predicting final course grade. So some special instructions for moderation involve centering. Centering is where you take your variable and you're going to move it to the zero as the middle. And this is really useful. It has two main purposes. And so you should put a star next to this if you're in my class, because this is always a quiz question. So when you're working with continuous variables, you want to center them. So generally we do mean centering. You could do z-scores, but I like mean centering better. And when you create that interaction, you're creating multicollinearity. So mean centering or z-scoring solves the problem of multicollinearity. It also helps with interpretation. So there's a two-part answer there. It helps with interpretation, and it helps deal with multicollinearity. Okay, so write that down. When those variables are not centered, it can become difficult because the b values, or maybe beta, can be negative, and then when you plot the graph, it looks positive. So you're figuring your graph won't match. It also means that when you center them, you can see what's happening. So centering really allows us to view the interaction. So what's going to happen is think about interactions and continuous variables as a small periscope of vision. So I love this submarine example, where you can only see a small line of data in front of you. What centering and simple slopes, when we get there in a little bit, allow us to do is to move the data around so that we can see it in this periscope. And so it allows us to look at like just the low end of the data or maybe just the high end of the data, and creates this view of the different areas of the data. Right? So what we don't do is median split somehow. So we're not creating groups. We're creating areas of the graph in a sense, but we don't make a low group and an average group. What we do instead is move the data around and pretend like everyone's taken down a notch or brought up a notch. So we'll get to that here a little bit more. It's probably the most confusing part about moderation is how that simple slope thing works. But centering really allows us to make simple slopes make sense. So it helps with interpretation. It also helps with multicollinearity. So the way we create that interaction is we multiply those scores together. And that's created after it's centered, and this will happen magically for you in QuantPsyc. So power for interactions isn't too difficult. So let's open up GPower here. And there's a couple of ways that we can do this, but if you're testing an interaction, you're really interested in is the interaction significant or otherwise why you're testing it, right? So we want t-test. And then we're going to do linear, multiple regression, single regression coefficient, because we're interested in the interactions PR squared, basically. We're going to use two tails, click determine, and we're going to use partial r squared. So how big do you think that interaction is? So in this particular example, I'm going to do a large effect size, so 0.25. calculate and transfer to main. Alpha is 0.05 for this course, 0.80 for power, being 1 minus beta. And you would think the number of predictors is 2, but you would be wrong because it's 1 for books, 1 for attendance, and 1 for the interaction. So it's actually 3. If you're working with categorical interactive variables, be sure that you just try to run the analysis first and look at how many dummy-coded categorical options you get, because there'll be more variables than you think. So you can always test this with fake data, or just remember that, let's say you have a dummy-coded variable with 3 levels, you'll get 2 predictors. So it's 2 predictors for one, 1 predictor for the other, and then an interaction of each of those. So it would be the 2 predictors for our fake dummy-coded variable, 1 for our second variable, and then 1 times both of those predictors, so 2 more for the interaction. I always find it best to create a fake example in R and just run it and see how many predictors pop out, just so I don't miss any. And if I hit enter here, a large effect size will tell me I only need 26 people. All right, let's work through this. Let's work through this bad boy, basically. So let me scroll up to the top here. I'm going to clear out all my mediation code that I was running, and let's load that data set. So looking at my master data set, there's no books by attendance column. That's going to get created as we go. So we're going to start by screening the non-centered, non-interactive data. So we're just going to screen all 3 of these columns as we normally would. All right. So first thing I'm going to do is check, make sure that I don't have any negative books or negative attendance or negative grades, and it's looking pretty good. And we're going to run this final model. And so here's another tricky point. Let me go back to my Word document here. Okay, so I know I don't have any missing data, blah, blah, blah. But what we're going to do is run that final model. So be sure you watch my regression video on data screening, because that's what we're doing here. And so we need all of the variables here. So what we're going to do is use the LM function for linear model for regression. DV is predicted by, check out this bad boy, scale here. That scale function is going to do the centering. Be sure you use scale equals false. We'll get there in 2 seconds. On scale again, turn that one off. Use scale equals false, and we're filling in X and M here. And so we're picking one of them to be the X variable and one of them to be the moderator. And that really does not matter the order that you put them in this particular example. If you watch one of my other examples, it might, but you just need to put in both of the variables here. Okay. We're going to use the scale function because it's centering. And so scale has 2 components. Generally, people think of scale, they just use scale general, like with no extra attributes or arguments. And that will create z-scores. So using center equals true and scale equals false creates mean-centered variables. Using center equals true and scale equals true creates z-scores. And this is the default. So line 3 here. Center equals true is the default, so I just kind of left it out. But you could put it in here, like right here. So we're just turning off the division by the standard deviation because we want mean-centered variables rather than z-scores. And by using mean-centers, we're going to match QuantPsyc's output. So we're just trying to make everything line up with the way that this package is going to help us out. But if you're doing this manually by hand as well, I'm just going to recommend mean-centered variables. That leaves the coefficient b in the scale of the data. Makes life much easier to interpret. You can also z-score them, but then the v-values become z-scores, so it becomes beta. So if you want beta, z-score the whole thing. If you want to keep b in the same scale of the data, leave it as scale equals false. So that was a lot of brouhaha here to get this set up, but I've done scale equals scale of books and scale of attendance. Now I just put my data here on a second line, and I've multiplied them together. That's going to create that interaction term for us. Okay. Not interested in the output yet because I am only doing that to get my numbers I need to run my assumptions. Right? So we're going to run Mahalanobis. I'm running Mahalanobis on the entire data set, no categorical variables. So I'm just going to use a data set, call means cove, all on the master data set. I'm going to create my cutoff score by using the number of columns that went into that. So that's 3 for our degrees of freedom. And then 1 minus 0.001 because that's our big important rule. Our cutoff score is 1627 with 3 degrees of freedom. Okay. So if you've been watching my regression videos for data screening, you'll remember that what this thing does is it creates a list of whether or not people are greater than the cutoff score. The as.numeric changes that to 0s and 1s, such that anyone who is an outlier gets marked as true, and anyone who is not an outlier gets marked as false. And that's going to be very handy here in a minute, because we're going to be able to add up how many outlier problems they have. So we're going to check people for Mahalanobis, Leverage, and Cooks, and we're going to use a baseball rule. So 2 strikes, you're out. And so if they mark on 2 pieces of outlierness, we're going to kick them out of the data set. By using this, by creating this bad Mahalanobis column of data or vector of data here, we're just keeping track. Okay, on the first outlier measure, nobody keyed in as an outlier. But we've saved it so that we can use it again here in a minute. Remember that leverage is a measure of how much influence somebody has on the slope. So think about this like cars, how much leverage do you need to get the car jacked up? And K here is going to be 3, just like power was 3. So we've got 1 for the books, 1 for the attendance, and 1 for the interaction. The leverage function we're going to use is hat values. We're going to create a cutoff score based on the number of predictors. So the formula is 2k plus 2 divided by n. Be sure you leave in our parentheses here so that you get the right order of operations. And the only thing I have to fill in here is k. So I haven't had to change anything below this k number here. So our cutoff scores are always going to be small positive numbers in the decimals, because it's telling you how much the slope has to change for someone to be an outlier. If you get large negative numbers, you've done something wrong mathematically. So our cutoff score in this example is 0.2, so people have to have a lot of influence on the slope because our sample size is kind of small. And so let's see here, we've got 3 people who would be considered an outlier on leverage, but no people on Mahalanobis. Now let's look at Cooks. Cooks is a measure of leverage and discrepancy, so we're going to do Cooks.distance. And all of this is being calculated on that output we created by running the final regression model. So there's no fake regression in this particular example. That's only for ANOVA type designs. For our cutoff score, whoops, come down here to Cooks, it's 4 divided by n minus k minus 1, which is degrees of freedom residual for our model. Okay. Our cutoff score is 0.11. I can tell I'm doing this right because it's close to leverage and it's small and positive. And I have no outliers on that particular measure. Right? And so if you haven't watched all these other videos, you can kind of scroll through and read all of the stuff I've got written about it here. But what do we do now? So what do I do with all of these? Wow, that says we have 4 outliers. We have no outliers. Cutting and pasting, not my friend. Here we go. So what does that mean? Well, now that I've got these 3 measures, I'm going to total them up and create an overall score. So it's kind of like you're batting one at a time. And so we at the end go, oh, you hit 2 strikes, you're out. Okay, or you hit 3 strikes and you're out. So we're creating a total score. And that top row, when we print out a table in R, is going to be the number in the data set. So it's going to be 0, 1, 2, or 3. If you get 4, 5, 6, 7, 8, or negative numbers, you've done something wrong. And the bottom row is the number of people who have that score. So when I do this here in a second in R, I'll see that I have 3 people who have 1 outlier mark. Now, people who have 2 or more problems are done, and so we don't really have any overall outliers. I can still create my no-out data set by subsetting my master data set, where anyone less than 2 gets to stay, and that actually just repeats the data set. That's okay, because now I really haven't had to change any of this code here. Now, if I had eliminated people, I would need to rerun my regression analysis, same as above, but with a no-out data set, so that I can screen my assumptions without outliers. Here it's going to be the same, but kind of keeping a tradition, I'm going to show you the code if it weren't the same, if we actually had outliers. No additivity necessary. Now, additivity would be necessary if you had control variables or other variables in the equation that weren't part of this interaction. You want to make sure that your variables don't go over 0.7 for suppression rules or 0.9 for multicollinearity rules. I've left the code in here so we can check those correlations, but at this moment I don't really need to. Okay. So no fake regression. We're going to set up our assumptions checks. Oh no, I accidentally hit the SPSS button. Well, that'll load in 20 minutes because it's very, very slow. Until then, we'll keep R'ing it up. So we're going to create our standardized or studentized residuals here. Those are z-scored to help with interpretation. So that's how far off we are at predicting people's scores. We're going to create our fitted values, the actual y-hat predicted scores, but I'm going to scale those as well so that they're in z-score format. That makes the next 3 tests much easier. So for normality here, now since there's nothing random, we should all get the same picture. This is a little problematic because it's slightly bimodal. Okay. I mean, like most of the data center between over 0 and between 2 and 2, so it's not super problematic, but this fact that this one is so low is not so good. So there is a bit of bimodalness in this data. If I look at linearity here, it's pretty good actually. It's a little squirrely, but mostly pretty good. Okay. You'll notice here that the number of dots, we have a small data set, so it might be causing some of our problems. Let's check homogeneity and homoscedasticity. So from this way, it ranges from about 2 to 2. We got one little dude hanging out here, but 2 to 2, pretty good. This way, it's 1 to 2, so that's not so great. Most of the data is between 1 and 1, though, so homogeneity is probably all right. For homoscedasticity, we're doing okay because all the dots have a fairly even spread here all the way across X. Remember, it's not across 0, it's across X. Right, so let's just see if we can get this to close. Oh, it's just hateful. All right, let's go back. Scroll, 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 scroll. So now that we're done, how do we actually run this analysis? Okay, you're gonna load that QuantPsyc library and run that moderation with the interaction. So we're actually just gonna now make it run the analysis that we've been screening. The nice thing about QuantPsyc is that it also gives you the simple slopes, so we don't have to create those manually, although I will talk a little bit about how that's done. Okay. So we're going to save this as model, and we're going to use the moderate.lm function. That is the function in the QuantPsyc package. And so the order you need to put this in is x, comma, m, comma, y, and then the name of the data set. Now, it doesn't order which one, it does not matter which one is X and which one is M, but you might have a hypothesis about which slopes you want to look at. So what's going to happen here is the M variable, I think, it's been a while since I've used QuantPsyc, is the one that's going to get split up. We'll find out as we go. I believe M is the one that gets split up. Yeah. Good grief. So reasons to never open SPSS. It takes 35 minutes to load and then hates on you because it doesn't think that it is legal. Because I'm not logged in at school. So here we are. Let's just try this in R and see what happens. Okay. So I'm going to load my QuantPsyc package. Okay. I'm going to run moderate.lm. So X, I chose attendance as my M. Y is grades, and then no outs our data set. Okay, we're going to run a summary of that, but to do that, I'm going to look over here so I can just see it a little bigger. Now, I hate the way this looks because I do wish this were a bit easier to read. So you do have to remember which one is which when you put them in. Okay. So MCX here is going to stand for mean centered. X stands for X. So whichever one you put in first. So in this particular example, we put in books. Okay, so let's now interpret that. Is that overall model significant? So our first question about just regression models in general, is the model, can we predict people's scores? So we would use the bottom here. This looks like our normal LM output. So 3 and 36 equals 8.07, p less than 0.01, r squared is 0.4. So we got a big effect size here. All right. Are the main effects significant? You can kind of think about that as main effects of ANOVA. So books, our x variable here, is significant. So b equals 4.15, and this is in the scale of the data. T, that 36 came from right here. Here's the T column, and it's 0.02. So for every one book, grade goes up 4 points after controlling for the other effects. Okay. So every book that you read gives you a 4-point increase on your grade. I would start reading, right? For attendance, which is going to be MCZ here, because MCM, I guess, was not a good way to write this, but it's 1.33. That T value is 2.37 with 36 degrees of freedom, and it puts 0.02, so it is also significant. So for every class you go to, your score goes up 1.33 points. I would also be going to class, be reading the books and going to class, because that's 5 points for every book and class combination. But we're really interested in that interaction. So the interaction is also significant because this is made up data, and we would say that B equals 0.73, T and P. Now, there's no way to interpret this particular B value. I can't say for every interactive point you get 0.73 points. That doesn't make sense. So just like in ANOVA, what we're going to do is break down that interaction by doing some sort of post hoc test. Okay. And what those are called is simple slopes. So in ANOVA, we did simple effects. Now we're going to talk about simple slopes. Simple slopes are kind of post hoc tests. But you don't want to think about these as creating groups. It'll kind of look like that in the output, and people kind of interpret it that way, but that is not actually mathematically what is happening. It does not separate people into like, you're in the low group, you're in the average group, you're in the high group, because that's like never a good idea to split your data that way. What happens is I'm going to create little mini regressions that pretend as if each person is on their current score, which is the average. We're going to pretend they're higher than their current score, so 1 standard deviation, or they're lower than their current score. Okay. So we mean centered these, so we started by looking at the average. So what happens when you read an average number of books, or you go to an average number of classes? But now then what we're going to do is pretend that each person goes and reads more than average books, or goes to more than average classes, and vice versa, less than average books or less than average classes. So can you switch X and M? Yep. If you don't like the X and M you get, just switch them. Okay. Go with theory and then go with interpretation, whichever interpretation is easier to explain. Okay. Now to run those simple slopes, we're going to use sim.slopes of our saved model output. We're using mean center, and we have to tell it what the name of the data set is. And which variable is M. So this is not literally $M, this is whichever one you picked as M. Okay. So this is actually where you could switch them. You don't have to switch them in the QuantPsyc package piece up here, all the way up here. You don't have to switch them here. You could always switch whichever one M is down here. Okay, finally got SPSS to stop crashing my computer. Let's go back over here to R. So we're going to do sim.slopes, and we're putting the model in. We're going to mean center attendance. I'm just saving those as just to save them, because I'm going to use them here in a minute for the graph. And we're going to tell it to show us simple. So let's look at that here in my Word document. What the heck does this mean? Right, so the AT on the side here is the fact that we picked attendance to be our moderator. And then we have the slopes for books at each level of attendance. So we've got low, mean, and high attendance, and then this is the slope for books. And the way that I can tell what the heck it is look at the average one, right? So I got 4.15. It should match the number from up here, okay? Because our main model that we already ran is the average one. So at average levels of attendance, the slope for books is 4.15. So if I am going to class an average amount of times, every book I read increases my score 4 points, right? So the INT here is the intercept, slope is B, SC is for standard error, LCL is for the lower confidence limit, UCL is for the upper confidence limit. This is essentially the confidence interval of B. Okay. And so we're going to interpret those slopes here. So at a average level of attendance, books is 4 points. So we already said that, right? At a low level of attendance, let's say you're not going to class at all, what happens is that books are only going to add 1 point to your score. So every one book that you read creates 1 point increase on your score because you're not going to class. Okay. As you increase the attendance, so at average levels of attendance, we get 4 points for every book. If I go to class a lot, so high levels of attendance, books gives me 7 points. So it's a multiplicative, I can't say that word, additive or multiplicative effect, right? So what's happening is that as attendance increases, the strength of the coefficient for books increases. So it's not that as you go to class more, you're reading more books. It's that as you go to class more, the importance of the books adds more and more to grades. So the relationship between books and grades goes up. It gets stronger as you go to class more. Okay. So how do I can tell if they're like significant, used to traditional significance testing? We're going to look at that confidence interval and make sure it does not cross 0. So both sides should be positive, both sides should be negative, nothing where one's negative and one's positive. Okay. So this last one here is probably not significant. If you are not really going to class, books are not helping you much. This one is significant. If you are going to class an average number of times, books is helping you 4 points. This one is also significant. If you're going to class a lot of times, then books is increasing your grade by a lot. Okay. And so I just have some interpretation here to help you really understand what's happening. But what I don't want you to think is that we created low, average, and high groups of attendance. What we really did, so go back to our periscope example. So we have this like periscope on a submarine where we can only see a small window in front of us. And what we've done is taken the data and moved that window of the data around so that we can see it in our window. So for people at low levels of attendance, what we actually did was shifted them up to see them. Because if you think about low's on the left, right? So negative scores or lower scores tend to be on the left. We had to move that to the right. So we had to shift them up to be able to see their scores. For high levels of attendance, we just sort of moved everybody down so we could see their scores. So we actually shifted them down. So one of the most confusing things about simple slopes is what's actually happening in the background is that for low levels of attendance, we added a standard deviation to everyone's score. We moved them all up so we could see them. For high levels of attendance, we subtracted a standard deviation from everyone's score and we kind of brought them down to the rest of our levels. So we're really just shifting the scores around the middle, but everybody. So it does not create groups. If that's the one thing you get out of this lecture, it does not create groups. It moves the scores around so that you can see what's happening at different levels of scores. So we're sort of pretending as if you don't go to class, and then pretending as if you do go to class and seeing what happens. Okay. All right. Now, sometimes you want like a good interpretation. Maybe a reviewer asks, what do you mean low, average, and high levels? So what you can do is run a mean and standard deviation on the moderator, so attendance here, and can tell that an average attendance is 14 points. And so people who are not going to class are going to class 10 times. People who are going to class a lot are going to class 18 times. Now, I don't love the graph on this. I really don't. But it's an easy graph to make just to look at to see that fan shape that you should get. Okay. So it's graph.mod. We're going to put in our saved simple slopes. And then it's x, y, yes, x, y data set. So there's no m in this particular code. Okay. So that's what it says here. Simple from our simple slope saved, x, y data set. What you want to do is then put in centered so that people know that the scores are centered, so you don't get when you see a negative score, you're not surprised. Number of books read, and YLab is what grade we made in class. So we're going to run that. And then what you do is you like click somewhere on the graph to put in the legend. Now here's one reason why I don't love this. Oh my God, why? But it's a really great just simple picture to make. You could also just hit finish over here. I think that's what I suggest in my for my course so that the legend isn't taking up the whole freaking picture. But either way, it does make a nice graph so you can kind of see what's happening. That's about the best I can do because the picture is so large. The dotted line is the average. The red line is low. The blue line is high. And so you can see it creates this nice fan effect. If the interaction is significant, you will see some sort of fan. The slopes will be different slopiness, or slopes will be different strengths. So they'll create a nice fan picture. If you get a parallel lines, they don't intersect, that implies that there is no interaction. Now they may not intersect on the picture, but they would intersect at some point. Here they actually cross, but let's say if you cut off this picture, they wouldn't cross, but they would at some point cross. Okay. But be sure you use this centered label down here, because otherwise people are going to think you read -2 books, and they're going to think that you've done something stupid. But that's because this variable is actually centered. So 0 here is an average number of books. And this is one book below average, 2 books below average, etc. And so I have an example right up here at the end. I did not include the little legend. That just explains how you might write one of these moderators up. They're actually pretty short, unless you got a real complicated model, because you end up talking about the overall model, the predictors, and then the simple slopes. Okay. So altogether, this is moderation using the QuantPsyc package.